All right, guys. So in this video, we are going to wrap things up for Chapter 5. We're going to talk about what's called Eulerizing and Semi-Eulerizing graphs. In other words, we're going to start to actually solve some of those application problems that we started off this chapter with. So, exhaustive routes. Let's first talk about this. We're going to use the term exhaustive route in order to describe a route that travels along the edges of a graph and passes through each and every edge of the graph at least once. Now, obviously, we've talked about Euler paths and circuits and what those are and how those work. Obviously, sometimes those aren't possible. We found some examples where you couldn't use an Euler path or circuit, so we're going to use this term of exhaustive route in order to describe where you go through every edge of the graph at least once, and sometimes more than once. So this is a kind of new definition, so make sure that you have that down somewhere. All right. So that's some information about exhaustive routes. One of the things that we're kind of looking at when we talk about exhaustive routes is the idea to minimize deadhead travel as much as possible. Basically what deadhead travel is, and we'll talk more about this as we go through some examples, are the extra passes, so the extra times that you are driving down a street or going down a path and stuff like that. So an easy way to think about that would be if we had snow plows and they were plowing the roads and doing their best to plow each road just once. Well, a deadhead travel would be if they had to go down a street that they had already plowed. Which sometimes that's helpful because maybe it snowed a little bit more, but a lot of times it's best to just do it once and not have to do it more than once. So that's what deadhead travel refers to. So when we want to do this, we talk about what's called Eulerizing a graph. So we're going to see basically how this works. The idea is that we're going to turn all of the odd vertices into even vertices by adding a duplicate edge and some of the strategic places. And when we do that, when we add these extra edges to our graph, we call that Eulerizing the graph. So again, another definition to make sure you've got copied down somewhere. All right. So to see an example of this, say we're looking at a 3x3 street grid. We've got an example of one right here where you've got quite a few vertices, A, B, C, D, E, F, G, H, I, J, K, L, as well as some vertices in the middle. So the first thing you would want to do when Eulerizing a graph is to identify all of the odd vertices. And what I've done for you and what this slide has done for you in this graph is they've gone ahead and labeled each of those odd vertices. So those are the ones with the red fill-ins on them. So B, C, E, F, H, I, K, and L. So the idea of Eulerizing is we're going to add an extra edge and try to connect those as best we can. And the easiest way to do that would be to just connect B to C, connect E to F, connect I to H, and connect L to K. And obviously when you do that, you're going to end up with a graph which now has all even vertices, because if you think about it, we didn't do anything to the even vertices, and for each of the odd vertices, like B started with a degree of 3, but now we've added this extra edge. It now has a degree of 4, and so does C. In other words, all of our odd vertices are now even, so our entire graph is even. And that's good because now we can make either an Euler circuit or an Euler path. Okay, let me go ahead and then actually in this next slide, I noticed that that's exactly what they did. I just went ahead and showed it to you first. Let me go ahead and restart OneNote so we can get rid of the extra stuff, and we'll get right back into it here. All right. So once we've done that, obviously this slide just shows you what the Euler path or Euler circuit would look like. So it's going from A to B, 1, 2, 3, 4, and you can kind of follow the numbers around. But you can see where adding those extra paths now allow us to do an Euler circuit where one was not possible before. Okay. So obviously when you do that, it ended up being a total length of 28, so if you did count your way all the way around, it ends up being 28 blocks that you'd have to cover. Now there are 24 blocks in the grid, plus you have an extra 4 deadhead blocks. So remember we talked about deadhead was where you were going on the same path more than once. So those 28 blocks are the original 24 plus an extra 4. In fact, that's kind of an optimal situation. If you think about it, there's no way that you could do better than 28. You had to add all 4 of those in order to get it to be a good graph. Now that changes when we make our graph a little bit bigger. So instead of going 3 by 3, we're going to look at one that's 4 by 4. Now this graph has 40 blocks in total and 12 odd vertices now. Remember before there were just 8. But here's going to be kind of the hard part, is now we need to figure out a way that we can connect our odd vertices. And for some it'll be easy, like obviously we can take B to C. The problem is we can't go from C to D, because if we do that, then B and D are okay. But now C is odd once again. Notice that it has 1, 2, 3, 4, 5 as its degree. So while the first one from B to C is okay, C to D isn't going to work. So it looks like from D, we're going to have to connect that to one of our other odd vertices, and the closest one is F. Remember though that you can only duplicate edges, you can't make new ones. So really when we're drawing this edge from B to C, it really just means that we're using this edge twice, okay? It doesn't mean that we're actually adding a new edge to our graph. So unfortunately we can't just go straight from D to F and add in a new line like this, or a new edge like this. Instead, what we're going to have to do is we're going to go from D down here to this vertex, and then from that vertex over to F. So you're actually going to have to add 2 edges to that part of our graph to make it work. Now notice that that's okay, because now D is going to be even 1, 2, 3, 4. F also has a degree of 4, and this vertex right here is going to be a degree of 6. It started as a degree of 4. We added 2 extra edges coming out of it, and so now we're okay because we do have even. Really, that's what you would then continue to do throughout the rest of your graph. If you can connect them directly, like G and H, we're good. Connect them here, J and K, we're good. But once again, when we get to L, we're going to have to do something similar to what we did between D and F. So we're going to have to go from L to this vertex, and then from that vertex over to L, or over to N, and then for O and P, we can just go directly there. So in other words, we started with 40 blocks, and it looks like we're going to have to repeat 1, 2, 3, 4, 5, 6, 7, 8 blocks. So it looks like we're going to have a total of 48 blocks that we're going to have to walk through in order to make sure that we walk through each block at least once. Which I'm going to assume the next couple of slides are going to kind of talk with you about what I just showed you, which is obviously, once again, for most of them, you can connect them directly, but obviously for D to F, you can't go directly from D to F. So instead, we're going to do something else. Obviously, too, you probably don't want to do it this way where you go from D all the way over to P. You definitely want to take the shortest possible route from that odd vertex to the next one. So then that's where you get the graph that looks like what I showed you. And once again, it just kind of reminds you that you go through 40 blocks plus an extra 8. Okay, so now open route problems are similar. Obviously, just like a path, we don't necessarily need to go through every path. We just need to get to all of our vertices. So, or we do need to go through every path, but we don't have to end back at the same place. And so remember, then it's okay to have 2 odd vertices. So when you're Eulerizing a graph, you're going to have all even. So when you totally Eulerize, so Eulerization, you have to have all even vertices when you're done. When you Semi-Eulerize, which is where you're looking for a path rather than a circuit, you can have up to 2 odd vertices. Now the rest have to be even. So for the most part, everything has to be even. With Semi-Eulerizing, you get to leave 2 of them as odd. So remember, when we Eulerize, we are trying to create a circuit, whereas when we Semi-Eulerize, we're just trying to come up with a path. And when we talk about circuits and paths, I mean Euler circuits and Euler paths. Okay. So again, that's going to be kind of what it'll talk to you about in these slides if you want to read through them. So Semi-Eulerization is what we use in order to create a path where we don't necessarily need to end up at the same place as where we started. For example, let's go ahead and go back to that 4x4 grid that we were talking about before. Let's say you were designing a parade route for 4th of July that you had to go through 40 blocks, but obviously with a parade, it's not necessarily important that you end up at the same place that you started. Remember, you can start somewhere and then end somewhere else. In fact, most of the time, that's how a parade works. And if that's the case, then we get to leave 2 odd vertices as odd. Again, it's already got those odd vertices labeled, so let's go ahead and start connecting. So we're going to go from B to C. Let's go ahead and connect D to F. And then we'll go ahead and actually, let's go ahead and fully Eulerize this graph. So we're going to go ahead and fully connect it like we did before. So obviously, this is what you would need to have for a circuit. But obviously, for a parade route or for a path, we get to leave 2 of them as being odd. So really what we can do is we can pick 2, and it would probably be best to either pick D and F or to pick N and L. Because obviously between those, you have to make sure that you are using 2 of them. So let's maybe use D and F, and we can get rid of those 2 paths. So now what we ended up with is all of our other vertices are even, but D is odd and F is odd. And so if all we needed was a path, then what we could do is we would start at one of those 2 vertices and end at the other. So again, it'll kind of talk you through that. What they chose to do was to start their parade route at B and to end at P. So same idea. They just chose to connect H and J down here in the bottom corner. And then to connect all the other ones directly. So you can kind of, obviously there's a lot of different ways you could go about doing that. Here's another example. Obviously this one is not optimal because you had to go through some extra parade routes or some extra paths that you wouldn't have otherwise, but there's one that would have worked. Okay, so Bridges of Madison County Part 2, we've obviously already seen an example of this before, but let's say that you got a photographer that needed to take photos of each of the 11 bridges in Madison County. So this is the graph of what that would look like. So you've got obviously the different bridges, and they're labeled there for you. So the Wilson, Truman, Hoover, Lincoln, Kennedy, Jefferson, and so on. And then obviously the places where there is land are labeled as R, A, B, C, D, and L. It turns out that there are 4 odd vertices. In fact, R is an odd vertex, L is an odd vertex, B is an odd vertex, and D is an odd vertex. So you've got these 4 as odd vertices. So depending on whether or not this photographer needs to start and end at the same place, or whether they just need to be able to start in one place and end somewhere else, is going to determine if we need to fully Eulerize this graph or to just semi-Eulerize. Okay, so now, again, how many and which ones that they're going to walk depends on the parameters. We're just going to use the fact that it costs $25 to cross each bridge. So at least you're going to be spending $275 to go across all 11 bridges. Now, obviously, again, you're probably going to have to go through some bridges more than once, so that's kind of the base cost. It's going to be more than that, but that's what it's going to cost at the very least. Okay, so now we get some more information. It tells us that the photographer needs to start and end his trip in the same place. If that's the case, then we need a full Eulerization of the graph, meaning we have to have all even vertices. And if you remember, we had 4 odd vertices, which were R, B, D, and L. So the best thing that we could probably do would be to connect them as closely as possible, which would mean connecting R to B one more time. So let's go ahead and draw in an extra path here. And then also connecting L to D one more time, so connecting this right here. Remember that the baseline cost was $275, and it looks like we're going to have to go through 2 extra bridges, so plus 2 extra bridges, and remember they cost $50 a piece, so that would be, or $25 a piece, so $50 in total is what I was meaning to say there. But yeah, if you add 2 multiplied by 25, which is 50, then you're going to come up with a total cost of $325 for an optimal route. So obviously this photographer is going to have to go over the Adams Bridge twice and either the Hoover or the Lincoln Bridge twice So obviously, if they're a photographer, they'll probably pick whichever one is prettier, whichever one takes better pictures or has better features, whatever that might be. So let's say instead that they had a little bit more freedom where they could start at one side and end at the other. So they were going to start their day maybe at R or L and then go from there. Then what becomes kind of nice is remember that you get to leave two odd vertices. And remember, so out of the four, you had 1, 2, 3, 4. Then really you only have to find a connection between two of those rather than all four. In which case, the easy way, there's a few different ways we could do that. We could go ahead and connect L to D. That would be doing the Adams bridge twice. We could also have done B to D. That would have been doing the Kennedy bridge twice. And again, that would give you two odd vertices at R and L. Or you could have picked either the Hoover bridge twice or the Lincoln bridge twice. So lots of different options depending on where this photographer wanted to start and where they wanted to end up. So let's say they had to start at B and had to end the trip at L. So we're going to start here, and they're going to end here, which means that these two odd vertices are going to be okay. But that means that now we have to somehow connect R to D. Remember, these were the two other odd vertices. So if you were going to start at B and end at L, now we have to get from D to R in as few spaces as possible. So that's going to probably mean that we're going to have to do the Kennedy bridge twice, and then either the Lincoln or the Hoover bridge twice. So now you're going to have to add two extra bridges for $25. It's still going to be $50 that you're adding. So once again, that optimal route ends up being $325. Okay, so let's go back to a previous example. If you remember, this was the one from the very beginning. We had a security guard who needed to patrol the streets for the Sunnyside subdivision. Here is what that looks like if you just look at the graph apart from all the blocks and all the other features. And so let's say they needed to, we're trying to come up with an optimal route. To make things easy, I've gone ahead and labeled all of the odd vertices so you can see all of those on the graph. So now, in order to optimize this, in order to Eulerize it, let's go ahead and remember, since it's a security guard, they want to patrol all of those. In fact, they need to get back to where they started as well. So really, let's think about the best way that we can do that. Probably these are pretty easy. In fact, anytime they're in pairs right next to each other, that makes it kind of nice. So then let's see. We could probably connect these two. We could connect these two as well. We've got pairs here and here. And then one last one here to here. And then obviously now we're kind of stuck because we have one odd vertex left and the starting point right here. So in order to make things work, what we'll probably have to do, in fact, I think this was also an odd vertex right here that wasn't labeled. So we'll just go from here to here. And then I think that should work for us. In fact, that's exactly what they had on their graph right here. So now we know how that security guard could work it out to have an optimal Eulerization. Okay. So obviously this answers that question from before. We've now made a optimized graph, an Eulerized graph. That obviously is not the route that would be taken. If you wanted to find the actual route that the security guard was going to use, then you would use Fleury's algorithm, which is what we talked about in 5.3, in order to find that route. Now, slightly different problem for our mail carrier. Remember, for our mail carrier, they're going to have to go down each street twice for the houses on either side. So this is what their graph looks like, a little bit different from our security guard. So if we're looking at this graph, actually taking a look at it, let's look at our degree of our vertices. We've got 2, 4, 4. This one is 6, 4, and then 2, 4, 4, 6, 4, and 2. So far, so good. They're all even. 4, 2, this one's 6. I'm just going to go around the edges first. So 4, 4, 2, 4, 6, 4, 4, and 2. And then these are 4. So actually at this point, our graph is looking pretty good so far. We haven't even found an odd vertex yet. But let's keep going. So these ones in the middle are 8. In fact, all of these in the middle are 8. And so actually, if you think about it, they've got all even vertices. So really, for the postal worker, there's already an Euler route that's possible. In fact, there's an Euler circuit that's possible. So really, we don't even need to go and worry about Eulerizing. It's actually already ready to go. So it turns out the solution to that was easier than we thought. We actually have an Euler or a Fleury's algorithm as well that we could use to find the route, but it looks like one is already possible without having to double back on any of the streets. All right, guys, that wraps things up for Chapter 5. We've now solved those street routing problems that we started off the chapter with. That kind of bookends the chapter nicely for us. We'll be getting ready for quiz very soon. Until next time, guys, have a great rest of your day.